It's my pleasure today to introduce Ed Stabler, professor at a truly excellent linguistics department at UCLA. At UCLA, Ed teaches all of the, he gets to teach all the good courses, stuff like natural language processing and computational phonology and mathematical linguistics and learnability theory. And I would say that almost everything he's interested in is something that a number of you here are also interested in. So what he's chosen to talk about today is the connection between minimalism, which is of interest to I think half the people here, dependency grammar, which is of interest to the other half. Most of Ed's work is about syntax, although as I said, he has done some work in computational phonology also, and in particular being able to put things into the right kinds of formal frameworks to be able to talk about them formally and computationally. The obligatory bit of background is that he did his PhD under Jerry Fodor in 1981 at MIT and spent some years doing various interesting things, including at IBM and ETS before winding up at UCLA in 1989 and being here ever since. It's my pleasure to introduce Ed Stabler.
Thank you. I'm interested in how human languages could be learned, and our only examples of human language learners that do it all well are humans. And humans are frightfully...
They don't learn so well either, apparently.
Yeah, they have lots of quirks we don't understand. Yet even the one-year-old versions are quite astounding. And so since I was thinking this wasn't really a linguistics talk, I thought I would describe in here at this occasion a strategy that I've been pursuing. Rather than trying to deal with the sometimes frightful complexity of human language acquisition, the strategy I've been pursuing with a few researchers recently is to try to understand how anything kind of similar to a human language could be learned by something with, much simpler than a human, but something which is, maybe similar to a human, just similar enough to be of some interest, but still maybe simple enough that we can get a grip on what's happening. So this is a strategy I might not dare to describe quite so frankly at a linguistics talk, but I thought I could get away with it here. We have this idea that human languages are learned by humans in context. That is, the child hears utterances of a language, and these utterances occur in a certain context, which is, perceptually and cognitively given. And so this is the kind of thing we'd like to study. The nice thing about studying it with robots is we can give the perceptual and cognitive context and keep it very simple and still see what even very simple mechanisms in that context might allow us to do. So this is the overall project, and I've been working on it for a couple of years, although I think there are no publications on it yet, but there will be some shortly. So I have some biologists working with me on this project as well. So the basic idea is the familiar one. So we're going to look at utterances, and there'll be English-like utterances in here, and in the examples I'll use it in this talk. And so there are many problems which come up right away. One is a segmentation problem. How do you segment the utterance? And this one I won't talk about. I'll just presume that we're looking at utterances which have been segmented. So we get utterances like this: John's eating cookies. And so we have elements which can be identified in some way, and they occur in certain configurations and not others. But more than this, in context, one might be able to recognize certain semantic properties of the utterance. And so one thing you might notice is, the utterance is complex. It's composed of a number of elements in a certain configuration. And so these elements can be changed for others with a corresponding change in semantic value, which would be evidenced by the kinds of contexts in which the different utterances would appear. So in an utterance like this, you can change in John for Bill, and this mean something different. So you would expect different contexts to be appropriate for one utterance as opposed to the other. You can change eat for buy, you can change cookie for pie, and so on. Also, the elements can be ordered in different ways, and the orders sometimes, in fact, often have different meanings. So you can say cookies, John's eating, or is John eating cookies, where the B is still almost completely reduced. And so configuration is relevant. So you not only hear the different configurations, but in a particular setting, you could imagine the learner reasoning about what these things mean. So one thing that's very striking, even at the first step, which rarely gets mentioned, is that these two kinds of changes in an utterance have very different kinds of correlated changes in semantic value. So when you change John for Bill, the sentence really says something different, right? It's about a different individual. But when you change the order of elements, there is a change in meaning, but it's quite different. So there are two very different kinds of influences on meanings, and one comes from choice of these elements, like John or Bill or whatever, eat or buy or whatever, and quite different are changes in configuration. And so these are semantically different, and characterizing exactly the nature of the difference is something I've been interested in for some years, but there's no human language where saying XY means John sings and saying YX means Mary sings, for example. That never happens. There is no language like this. Changes in configuration never signal that kind of change in meaning. It's always something different. It's actually more similar to the meaning contributions that affixes make. The contribution of configuration is more similar to the contribution of affixes, yeah.
Mary loves John, John loves Mary. That's a configuration change.
Yes.
A really different meaning.
Yes, yeah, that's right, yeah. So yeah, there is this kind of meaning change, but yes, so still it's true that there's no language where Mary sings, where XY means Mary sings, and YX means...
XY. So you only made the statement about...
I think I took two words, and I just reversed them.
I see, okay.
And yeah, so the reversal so reversing two elements never introduces, a name for a completely new element. This doesn't happen, yeah.
So, just to propose another possible counterexample, there are some adjectives in French which mean different things,
Yes.
whether they're before or after the noun.
Yeah, that's right. Yeah, the things are often related, but yeah, that is a more serious and interesting kind of counterexample. Yeah, and there are theories about how that should work. But anyway, this is just introductory remarks. I haven't gotten to the serious stuff yet, but I wanted to point out that there's something...
This tradition, Harold.
Yes, there's something interesting we notice right away, a very basic thing, which we'd like to understand. And yeah, I don't know of an adequate account of these matters yet. But yeah, certainly this is something we'd like to understand. And yeah, the strategy I'll take is to imagine that the learner conceivably can recognize things, so the learner of a language can conceivably recognize more than just the serial order of elements in a language, right? So the learner has possibly more information about what's going on in the language. So then the learning problem can be divided into two stages. One where you recognize certain kinds of possibly semantic and other relations among the elements besides just occurs immediately before, and a following stage which where you identify the whole set of patterns of this kind that the language allows. So this is the strategy I'll take, but we'll start by using some standard ideas from formal learning theory, where most of the work has been on learning string sets just from strings. So just to review some things. So there's a very simple approach to learning string sets, which many of you are no doubt familiar with. This is probably the simplest way to formally capture the learning situation. We just imagine, so we idealize in quite a few respects in order to just get a first idea about what could happen in learning and what kinds of things might be learned. So the first results I'll talk about, imagine the evidence that's presented to the learner to be an infinite sequence of elements, sentences of some language, and we imagine this infinite sequence has all and only sentences of the language. So this kind of a object is sometimes called a text. So we'll imagine learners that look at longer and longer finite initial segments of a text, and at each point they can make a guess about the language. So their guesses will be grammars.
Or means that there isn't an element of L which is not contained in,
that's right.
in that sequence.
That's
so
right.
It's a total list.
It's a total list, but they can be in any order, and you can repeat things and so on. But every single expression of the language occurs at some finite point in the list. So we imagine the languages are enumerable as usual. So the learner, however, sees just finitely much stuff at each point, and the learner's job is to guess a grammar that guesses everything in the whole list. So in some cases, the language will be infinite, and so the learner is still faced with the problem of guessing a potentially infinite set from a finite sample of it. So we say one criterion for success in this setting is if the learner seeing larger and larger initial segments of a text, if the learner actually converges on a particular value which doesn't change ever, and if that value is in fact one that generates the language of the text, then we say the language has been identified, or the text has been identified. So we'll call a language learnable if there is some learner, so a learner is now just a function of this kind, if there is some learner that can identify that language from any text for the language. So again, there's a, this requirement means that you can't, for example, code what grammar you want to have the learner guess by, particular orders of the elements in the language. You need to be able to guess the language for any text.
But not in finite time.
Always the learner is looking at finite initial segments, but we don't put any particular finite bound on how far the learner needs to go. We just require that there will be a finite point that the learner will converge, and from then on, with longer and longer segments of that text, the learner will continue to make the same guess, so that's convergence, and the guess is correct.
And when you say any text, you're meaning any reordering of this otherwise single text.
Right, reordering and introduction of redundancies, and so there can be redundancies and reorderings, right?
And the finite amount of time that you take may depend on that particular text, but it's finite.
Of course, right, yes. So this is the setup which was described by Bolt many years ago, and he showed that with this, in this setup, no proper superset of the class of finite languages can be learned in this sense. That is, it's easy to define a learner which will guess every finite language. All the learner needs to do is to guess at each point that it's seen everything. So the learner just guesses the set of sentences seen so far, and eventually, if the language is in fact finite, that guess will be correct and will never change with extensions of the initial segment. So it's clear that class of finite languages, which is an infinite class, that class can be learned by a learner that just doesn't generalize at all. But no proper superset of this can be learned. And this is a strong negative result. It means, nothing in the Chomsky hierarchy above the finite languages, so the regular languages and anything that include them, none of these classes can be learned in this sense of learning. Intuitively, the idea is if all the finite languages are included in the class of possible languages to be learned, no matter how much evidence you get, there's never a basis for generalization, right? If you see A and AA and AAA, you might guess, oh, it's the language of all A's, but this guess is no good in a setting where it could just be the language that has just those three strings and no others. So this learning setup has been studied very extensively, and in 1980, Dana England proved this result, which characterizes the learnable languages in a non-trivial way. So a class of languages is learnable in this setup, just in case every language has a certain property. Every language has to have a finite subset such that there's no other language in the class that includes that subset, but which is properly included in the language in the target language. So for every language L, there's a finite subset where there's no other language in the target class that is a proper subset of L that includes that finite subset. So this, it turns out, is a perfect characterization of the learnable classes. And this characterization has been the basis for quite a few results. So most of the learning results in this tradition are negative, as the start might have indicated, but in fact it turned out to be true. You can get a book that's full of negative results about this kind of learning setup. It's just too hard. Even though we give the learner all the evidence, we don't even require that the learner be a computable function, still this identification criterion is a very tough one to meet. But there is one strain of, one line of positive results which has been quite interesting, and it began with an idea of England's. So England characterized a set which, in the Chomsky hierarchy, so here I have, in case you can't see, the finite languages, the regular and the context-free. So she characterized a set of regular languages that include some finite languages, but it's a strict, proper subset of the regular languages that have this property. So these languages have the property that if you have two strings in the language where the two strings have a common suffix, then, so if you have two prefixes for the common suffix in the language, so XZ and YZ are both in your language, then those two prefixes have all the same common suffixes. That is, for any string you take, this should actually be strings from, yeah, this is right. Yeah, so for any string you take, if XW is in the language, then YW is in the language. So for those of you who fiddle with regular languages, you know the set of good tails of a string, the set of good suffixes characterizes a state in the canonical acceptor for these languages. So in effect, if you find any string which is a common suffix for two prefixes, that perfectly characterizes, in effect, the category of those prefixes. So if you have this property, it turns out that the class of languages is learnable. And so this is an infinite class, and it can be relaxed. So this characterization actually defines, I think, zero reversibility, but you can weaken it by allowing the learner to classify things by not just a common tail, but you impose requirements on the ends of the prefixes, in effect, allowing the learner to look back into the prefix a little bit. But this idea turned out to be very fruitful, and it was developed by Kanazawa in a Stanford thesis. So he noticed that a very similar kind of strategy could be used to identify the languages of simple categorical grammars if they're k-valued, where this means that if each pronounced lexical element has at most k syntactic categories. So again, it's a kind of non-ambiguity requirement. It says, so in the case of one, so a simple unambiguous language would be one value. This is a language where each word has at most one syntactic category. And so you can classify a word based on its syntactic category, and you know every other occurrence of that word will have the same category. So this property, which he called rigidity, gives us a class of languages which is more interesting than the reversible languages that England considered. It extends into the context-free class, so it contains some finite languages, some regular languages that aren't finite, and some context-free languages that aren't regular. So this class is more interesting. Still, it doesn't go far enough to account for the kinds of patterns we have in.
I don't know what heavy bracket is.
So this is, I'll show you, I use this idea too, so I'll show it to you in a minute, but the idea is in these categorial grammars, if you draw the derivation, and bracket constituents in the derivation, the brackets always include just two elements. So you have a functor and an argument. So a headed bracketing is just where you have the bracketing, but you also, in addition to providing the brackets, you specify which of the two elements inside those brackets is the head. That is, which took the other as argument into it. They're sometimes called function argument structures. But we'll see examples of this in a second.
But the claim is that you can also learn this from strings.
You can learn it from strings as well.
Right.
But yeah, the algorithm from bracketings is extremely simple, and this is the one I'll rely on here in the following development. So since this class is still strictly included in the context-free languages, we can't capture the kinds of you can't capture the kinds of the sets of strings we'd like to capture, but more than that, you can't capture the kinds of dependencies among lexical elements you'd like to have in a grammar for a human language. So this is familiar to everyone probably, but let me just quickly say, in human languages we find kinds of relations which are sometimes called copying or crossing relations. So you can say the horses teach feed, where the man is the subject of teach, and feed takes horses as its object, and so what did I say? The man Hans the horses teach feed. This is the translation. So anyway, you have the subject 1 and subject 2, and then verb 1 and verb 2 in this crossing kind of order. So we'd like to get these kinds of dependencies, which I've shown informally with the arrows, and also we'd like to be able to get languages like this simple copying language.
I'm sorry, what is being asserted here? I mean, you gave it, I suppose it's Dutch or something.
Yes.
And what does it say?
So what I'm saying is that in human languages, we find this kind of dependency structure, where the dependencies are crossing.
Yeah.
That's all.
It's nothing to do with the fact that there are two things or anything, it's just that they cross.
Right, they cross, and you can have unbound. You can have subject 1, subject 2, subject 3, verb 1, verb 2, verb 3 in this order, where the dependencies between the subjects and verbs are crossing. And so this is the basis of of string-based arguments, where you can find certain languages where these dependencies are syntactically marked and show that the string languages in those cases cannot be generated by context-free languages or context-free grammars.
And is this like a respectively construction?
Yes, like respectively. We also get analyses like this one. So this is Hungarian. So I won't try to read it, but I'll just look at the pattern here and the analysis. So the analysis here is controversial. There are alternative proposals, but one proposal says that you can have verb clusters like this in Hungarian, where you have 1, 2, 3, and then a particle, home, some kind of special particle, and then another verb. So you can have 1, 2, 3 particle verb. in this order. But then it looks like these two can hop over the last verb and appear here. You can also get 1, 2, particle 4, 3. And then it looks like these can hop over that second verb and appear here. So if you write a grammar which allows you to roll things up this way, those grammars can generate counting dependencies of unbounded complexity. So we call this kind of grammar where you have NAs, NBs, and NCs. We'll call this a language with 3 counting dependencies. It turns out if you have a grammar with a mechanism which explicitly allows this kind of rolling up derivation, it's easy to define languages with any number of dependencies, counting dependencies like this. So you can have 3 or 5 or 10 or however many. And so these languages are not context-free, and when you get over 4 counting dependencies, they're not even languages that can be defined by tree-adjoining grammars. But the whole class, there are variants of tree-adjoining grammars that can define the whole class. And those variants have been proposed for scrambling and other things in the TED tradition. So in English, we have various kinds of mixed dependencies, and if we wanted our syntax to actually directly show these kinds of dependencies, it would be tricky to do as well. So I'm not making any formal claim there, but we'd like to have a syntax which lets us read off the semantics as easily as possible. So we'd like to have something more expressive than simple A-B categorial grammars, and so I'll now propose such a system. So the grammars I'll describe I'll call minimalist grammars. They probably shouldn't be called this, but I made the mistake of calling them this 6 or 7 years ago, and so now I don't want to change. But anyway, they're inspired by the minimalist tradition in syntax, the Chomskyan syntax that began around 93 or something. And one of the initial motivations for this tradition was to strip away a lot of the mechanisms and try to make do with something less. So I liked that idea and proposed this formalism around that time. So these grammars have just 2 mechanisms, or 2 parts. A grammar has a lexicon, and then you have 2 structure building functions which can build structures from your lexicon. A lexicon is finite, and each element in the lexicon is also finite. It's a finite sequence of features, and the features have these 4 kinds. You can have categories and things that select those categories. So you can have nouns. You can have things that select nouns, meaning they want to take them as object or whatever. You can also have licensors, WH licensors, and things that need WH licensing. And so I'll explain how these work in a minute. But we have just these 4 kinds of features indicated in these ways, and then we have phonetic and semantic properties, which I'll just use the string to indicate. So these grammars have these 2 structure building operations, which I can describe informally this way. The basic idea is pretty simple, and they've been explicitly laid out in a number of places. But you could have 2 lexical items like this. So this is kisses, and it's a verb, and it has these 2 features equal D, and each one indicates that it wants to select a determiner phrase. So this is a simple idea of what a transitive verb might look like. It wants 2 determiner phrases as arguments. And merge is defined in such a way that the first thing merged will be merged on the right, that is concatenated on the right, whereas any following things merged will be attached on the left. So if we combine kisses with something of the appropriate category like Pierre, we will get a structure like this, where the selector and the thing selected, these features cancel each other, like in categorial grammar. So, and we form this structure where kisses is ordered before Pierre. But if you have a structure which is already complex, so making here is already combined with tortillas, but it still wants to select another determiner phrase, if it combines with one, that second one is attached on the left, they say, specifier position. So we get little structures like this where the elements are ordered, and each operation checks a pair of features.
And that little arrow at the node points toward the head, right?
Right,
Like-
these are kind of bare grammar notation where instead of labeling this DP, Jason should give this talk. I use an arrow to point to the head of the category. So we see this is a verb phrase. This is still a verb phrase because if you follow the arrows down, they still point.
I'm not sure now about, before kisses got the D,
Yes.
now making gets the D. Is this correct? Or am I reading it wrong?
So this is a lexical item.
I thought, I'm sorry, I thought that the red D
Yeah.
is all that kisses gets.
No. So this is kisses. It wants two Ds. I could have had this be, I probably should have had this be kisses Pierre. The only reason I put this in red is to draw your attention to it. So these two features, the redness just means pay attention to me because I'm getting
So what does kisses have? It doesn't have the red D, it has the GV.
No, it has three features.
It
I'm
has
drawing
three
your
features.
attention to the one that gets
Aha.
So we start with two lexical items that have a total of 4 features
I
here.
see.
The result cancels 2 features, so we have 2 left. Here we have a total of 3 features going in and 1 left at the end because each operation cancels a pair of features. And I put the ones in red that were being canceled because I wanted, this is an important property.
And how do we know that Maria is going to be on top?
We stipulate, this is the definition of merge. We stipulate what happens when you have something of this category that's combining with something else which already is complex. If it's already complex, anything it attaches with merge gets put on the left.
I see.
So that's why.
So the first D to meet kisses will go on the right.
Right,
The second one to meet whatever is built up will go on the left.
Exactly.
Do you have to peel off the features in that order?
Yes, features are always checked in left to right order. And they're always, so we think of this function as always applying to 2 elements. This is a binary function on expressions, and it always applies to 2 elements, always checks the first feature of the head of the first argument, and the first feature of the head of the second argument is always what gets checked. Yeah?
Do you have a way to distinguish between the 2 classes of transitives?
Yes, I do, yes. We should maybe leave this to discussion period though. So I'm not trying to present a realistic grammar here, but just to show how the mechanisms work. So there's one other operation which is unary. It doesn't combine 2 things, but it simplifies something in effect. So if you have a structure like this, where, so this we see is headed by this element, which has category T for tense. So if you have a tense phrase that looks like this, it has a plus case feature. You search the tree to find one element which has a corresponding minus feature. Then you take the phrase that has this as its head. So the phrase that has that as its head will be the largest subtree that has this as its head. In this case, it's just Maria. So notice speak Nawa has speak as its head, but speak Nawa is not the phrase because there's a larger phrase here. Maria speak Nawa, that whole thing has speak as its head. And that is a phrase because there's no larger subtree that has speak as its head. So this is in effect, the verb phrase, Maria speak Nawa. And so the way movement works, it always moves phrases, and the way it operates is if you have a plus F for some F, you find a minus F phrase, and you take it from its current position and put it up to the left. That's it. So these grammars turn out to be quite powerful, and they can do lots of things. They can capture many kind of traditional analyses in the Chomskyan tradition. So I won't show a traditional analysis because they tend to be rather complex, but here's a lexicon with 7 lexical items. This lexicon generates an infinite language because we have 2 transitive verbs. We have a tense marker, the affix S, so this minus is just to indicate that the string is affixal. We have an empty string which has the category of a little b, a kind of transitivizer category. We have two determiner phrases in the lexicon, which are names that need to have case assigned to them. So this grammar generates, Beatrice criticizes Beatrice, Beatrice criticizes Beatrice, and Benedict criticizes Beatrice, and so it has the recursive category that forms a tense phrase from two others. And so this is a tiny little grammar, and the structures, the rules I showed generate structures like this, but it's an easy matter to show them in a more traditional linguistic form like this, where we have used X bar theory, so we have a tense phrase at the top here, which is explicit in this kind of drawing, and so this is the kind of thing linguists usually look at. But this is the notation I introduced. And actually we have a number of equivalent notations, and the one that's mathematically most useful is one where the expressions are not in trees at all, but just the expressions are categorized tuples of strings. So here, this is a derivation, the very same derivation I showed on the previous slide, where we derived Beatrice criticizes Benedict as a tense phrase. And inside of this derivation, so each binary branching is a merge step, and each unary branching is a move step. So in this number of steps, we derive the string, and this is a completely explicit representation.
So where did we start, at the bottom, or?
Doesn't matter where you start, actually. You can, the way linguists usually describe it, you start at the bottom and start doing merges, but it's very easy to write an equivalent grammar that starts at the top and does expansions. There are lots of ways to represent this kind of grammar.
Question, in the two examples of moving things that you showed us, the thing that got moved was not the head.
That's right.
Is that something you insist on, or?
Yes, but it doesn't have to be stipulated, because movement only happens when you have an expression whose head has plus f as its first feature. And the thing that's moved is always an expression that has minus f as its first feature on its head. So that just follows. So in these derivations, all of them, every step cancels a pair of features. So we can see here the d and the equal d cancel and don't remain, and so on, all the way up. So every step here cancels a pair of features, and we end up with just one, which we think of as the start category or whatever. So here I imagine tense as the start category. So this kind of grammar is interesting. It generates quite a lot of different kinds of structures, and the derivations can also be looked at this way. So we have that previous derivation had just 5 lexical items, and each step just checked a pair of features. So the entire derivation can be depicted by this very simple graph, where we just show which feature checks which other feature on another lexical item. So this graph shows the entire derivation from the previous slide. If you spell out what each of these checking relations amounts to, you get exactly the picture on the previous slide. So the structure of the derivation is extremely simple. So I call this a matching graph. One thing I like about this graph is it looks almost like what we'd like to have in a good grammar is one where the syntactic relations, the checking relations, correspond to semantic ones. So here we almost have this. So phrase is most immediately related to its object, Benedict. And there's a transitivizer here which relates praise and the subject, Beatrice. And outside of all of that, you have the tense coming. The tense saying, this whole thing occurs in the present or whatever. So this is almost a semantic dependency structure, but it's enriched with all this syntactic information. So imagine we strip this syntactic information out and get I don't know whether you can see this, but I want to have both on the same slide so I could show you the relation. So if we take a matching graph like this and just remove all the syntactic features and all the orders on the incoming arcs, but we keep the order on the outgoing arcs, we get a structure that looks like this. So I numbered these arcs my graph drawing tool numbers the arcs in case you don't have color. But with color, all the arcs labeled 1, these are the first outgoing arcs.
Which is it on the dark?
So this is the first element. So
Is the blue red?
so first is red,
Uh-huh.
second is blue, third is green.
I see.
So this is the very same graph, except I stripped out some information. So this is now closer to a dependency graph. I'll show you a bigger picture on the next slide. That's so I guess I don't show it to you on the next slide. Yeah, this is it. Yeah. So here's the very same picture. I'm afraid you can't see this maybe. So this is the affix S, the tense marker, and it's connected by dependencies to the transitivizer, which relates the subject and the verb is connected to the object.
The S is also related to the subject because it checks cases.
Right, yes. So the red arrows always indicate selection. The second arcs always indicate licensing relations. So this is getting closer still to a something which we could imagine could be recognized, relations that you could imagine being recognized on the basis of semantic analyses of a language. And so this was my idea. So this is the idea I'll pursue here. So imagine that the learner could recognize relations something like this, and
These are syntactic relations, right? They're not semantic.
these are semantic relations. The verb is connected to its object. The verbs, so it's actually a mix. So I'll come back to this. It's a mix, but the semantic relations are the red ones. You know, the red ones are semantic relations, clearly. The case marking and things like this is
So
a mix.
what is the name it? Or?
Yeah, well, selects is the way we name it in the Chomskyan tradition, but the verb takes its object. And so, what semantic role the object of a verb takes depends on the verb, but it could be named. So here's the problem I'd like to consider. I need to go quickly now, but it's now we're to the easy part. So suppose the learner was able to recognize relations like this on strings. Then could the learner identify grammars like this, right? So suppose a speaker has grammars like this and produces utterances in context, and the learner were able to identify relations among the elements of the utterance like this one. So now I've broken the problem into two pieces. First, we have to imagine the learner getting from the string in context to a graph like this, and then given a set of graphs like this, getting from such a set, a finite set, to a grammar that generates an infinite set of graphs. So this is the problem I'll explore a little bit. So it turns out...
We're still in the string situation. I mean, when you started out, you had this list of all the possible sentences.
Right.
And
So
you're
now...
going to use this as a tool.
So now the way I'm going to imagine the learning problems, so there are actually two learning problems. One of them is where you have an infinite sequence, not of strings, but of structures like this. And the goal is to get from that set of structures to a grammar that generates exactly that set. So the other idea I'll use from Kanazawa and Anglin is a kind of non-ambiguity requirement. So I'll say that this grammar is one valued. The reason is each string is assigned at most one categorization. It has at most one, so a categorization is given by a sequence of features. Each string has at most one syntactic category. So I'll call this grammar one valued or rigid. So first problem, can rigid minimalist grammars like this be learned from texts of structures like this? So this problem has the familiar kind of structure, but generalizes the Kanazawa result in a useful way. So this class of rigid minimalist grammars extends into the context-sensitive class. So it has copying, it has rolling up, it has all of those patterns which I mentioned earlier. So it can generate simple copying languages like XX. It can generate simple counting dependencies like A to the n, B to the n, C to the n, D to the n, E to the n. But it has also, bunches of things from the Chomskyan tradition which can be coded up in this kind of formalism. So we get a class that looks like this. It does not include all the finite languages, but it includes some regular, some context-free, and some non-context-free, but still mildly context-sensitive languages. Yeah.
Doesn't it include all the k-reversible languages, and is the k the same?
No, the k is not the same, and I haven't studied this question. My hunch is no. I think it doesn't. But it's a different dimension that we're keying off of. But yeah, the role in the learning strategy is similar, but it's a different dimension of structural complexity that we're using.
How does all these languages do extend English?
No, I don't think
They don't do it either.
I don't think so.
Okay, thanks.
Okay, so this looks like maybe we're moving in the right direction. The setup is a bit artificial, but maybe it's in the right direction. It turns out the k-valued minimalist languages can be learned from those structures. So I'll show you quickly how the learner works. It's very simple. So imagine you get a structure like this. So just one structure. So the structure shows you these elements and some relations, and you need to infer what grammar generated this structure. So you have no categorical information there. That's what you need to recover. And so here's the algorithm. You label the root with the start category. So you pick a start category, call it T. You then can identify the incoming arcs of the non-root nodes, and each of those, the first ones coming in, these each have to check category symbols. Take my word for it. The first thing you have checked when you enter a derivation is your category. Then all other incoming arcs have to check licensee features. Then you're done, basically. Then all the outgoing arcs are checking either categories or licensee features. And so let me just emphasize one thing that was going on here. When I add the root category is stipulated, but all other categories, I just made up a new one each time. So I just said, D, E, F, G for the categories. We don't know what they are, I know there's one. And then when I needed the licensee features, I just made some up, all new, H, I, J, and so on. You just go this way, just making some up. So this is actually a completed graph. It's a completed matching graph in the sense that if you take these as lexical items in a grammar, that grammar generates this structure, and in fact, no other structure. So if we just take the lexical items out to get this grammar is already rigid. So this grammar is called in the literature the general form grammar for the text. It already is rigid, so if it weren't rigid, we would unify symbols in order to make it rigid. So I'll show you how this works in just a minute. But if we compare this grammar with this one, the target grammar, you can see it's close. It's missing and. No surprise, there was no and in there. It hasn't figured out that Beatrice and Benedict are the same category. So it's different in a number of respects, but similar. So suppose we give the learner one more structure. So the language generates Beatrice criticizes Benedict, and Benedict praises Beatrice. This structure, if we go through those same labeling steps and collect the lexical items out, we get this much larger grammar. Now this one isn't rigid because Beatrice has several categories, P, S, D. But we know the target is rigid. So what we do is we just unify those three categories. We equate them, make them all the same, and do that whenever we have more than one assignment of features to a category. And so before we do this grammar generates exactly two structures, namely the ones we saw. And after we do it, we have this grammar, which is an alphabetic variant of the target. So on the basis of two structures, this learning strategy has identified a recursive category that generates an infinite language. Yeah.
Have you unified the licensing features?
So if the unification will always be, minus F and minus G. You just replace F by G. It's just a substitution.
I may still be misunderstanding the requirement of rigidity.
So rigidity just means so criticize actually in English is probably ambiguous. You can say, you criticize, he praises, right? Or you criticize.
So by rigid, you mean one lexical entry per item?
One syntactic categorization, right? One lexical entry per string.
Okay, so this forces you to unify it.
Right. Yes. So this learning strategy can be applied to grammars that generate copying languages. I won't go through them. Grammars that, like this one, generates 5 counting dependencies, and it works. So we just recently proved these theorems. So in fact, you can show that it always works. This learning strategy, where you get a text of these dependency structures of just this sort, if you get these texts, we can prove that in the limit, you'll eventually converge on a grammar, and that grammar will actually be an alphabetic variant of the target. If the target is reduced, meaning there are no useless lexical items in there, right? None. So you can't have lexical items that don't appear in any derivation and certain things like this. So this learnability result extends Kanazawa's into the class of mildly context-sensitive grammars. So just quickly, let me respond to the so what questions. So there are three big kinds of so what questions. One is why, this result is only really relevant or interesting if learners can really perceive the relations that I mentioned, that I defined in these D structures. The relevance to human language learning is only there if somehow you can have some kind of dimension like this bounded ambiguity. And the learnability result we have here is of this very primitive kind. You know that the learner will converge on a correct grammar, but you don't know when, right after some finite time. So that's not a very nice guarantee, and we don't know whether, we haven't said anything about whether this learner is computable or anything like that. We just know there is such a function. So I'll quickly respond to these by way of concluding. So the semantic dependencies in a graph like this, I think actually can be identified, at least in certain restricted settings. So this is a funny kind of problem because this is the connection between what you can perceive or think and what and this graph, right? So this is where we are making assumptions about what a learner could figure out. And so in a robotic setting, we've made this work. But the idea is the selection relations, the primary ones, these can be recognized by identifying the cognitively salient events and participants. So what this means for a child is hard to say, but we can fix a robot where we have a teacher robot and a child robot. We can just fix things so that the events the one robot thinks are important in its perceptual environment are the same as the ones the other does. So we have in fact cooked up robots that do this. The other relations always are indicated, these are all movement relations, and they're always indicated by a change in string position. So selection is always local. If you see something selected which is not in its local position, you know it moved. And so we can get those as well.
Same.
So when you merge with something, you always put the first thing on right, and the second thing on your left.
Okay.
And if it's not there, right, if you know what the subject was and it's not where it should be, you know it moved. And so these relations can be identified in certain cases from this. So we don't have a formal result here. In fact, it's quite tricky to set up a formal result because this involves, definitions of what's salient, what's perceptible, and so on. But this is something we're working on now. So let me just quickly go through these things. So there's a little wrinkle in this which is more interesting. So the tense marking, this is, if you just have a robot, so our robots, they look at network events as recorded in logs. And so you have, the machine Beatrice pings this other machine, and you have some log record of this or whatever. So the temporal relationships between these events and the time of utterance, these are certainly more abstract. So we could imagine that a learner began with recognizing just, say, subject argument or predicate argument relations, and the tense comes in later. If you do this, what happens is the grammar the learner will generate is going to generate strings that aren't in the language of the sample often. So you might generate things like praise Benedict or Beatrice praise Benedict, even though you never hear praise without an affix in the input sample. And this might be a good thing. But anyway, these are the things we're playing with. Let me turn quickly to the k-valuedness assumption. So this is a bound on the degree of syntactic ambiguity of elements. So in the grammars I had, so I've actually built a grammar in this formalism for an introduction to syntax, which is used at UCLA. And so looking through this grammar for where one valuedness is not satisfied, we find various kinds of cases. So the affix S can be a tense marker, it can be the plural marker, it can be a definitive case marker. So this is, violates the one assignment idea. The empty element, it can be a transitivizer, be a complementizer, various other things. Re can appear intransitively. Transitively can also appear as a noun, that was a good read or something. Same for other things. So these two seem to divide again because these elements, these are grammatical formatives. There's no other, we saw this in the first slides, if you take John's eating cookies, that first "is" in John's eating cookies cannot be replaced by anything else. This element is a syntactic element that has a role that no other element has. It's a grammatical constant in a certain sense, which can be defined. So these are, it turns out all of these are grammatical constants, whereas there are other elements like read, which aren't grammatical constants. They can be replaced by other things. But the thing about all of these cases which makes me think that they are not two different kinds, but all the same thing, is they all mean different things. So all of these things have different semantic types. So when I originally introduced the formalism, I said this part is supposed to represent the phonetic and semantic features. So if we pull apart the phonetic, that is the orthographic and semantic features, and represent semantic types in the lexical item, so if we enrich them so that they have, say an orthography and a semantic type, suddenly the grammar here is no longer ambiguous. So there's a hope that the syntactic ambiguity is resolved in a grammar that distinguishes elements based on semantic properties. As for feasibility, this is a place where we're working now. The path has been explored in a number of other simpler problems. So again, we can try to follow the lead of those. So in the case of the K-reversible languages, there have been a number of attempts to show that these languages are pack identifiable. So this is a learning framework introduced by Valiant in the 70s, I think, and it's probably approximately correct. So you imagine there's a distribution over the sampling space, and you draw some number of samples from this space and try to conjecture a grammar for the concept that you're learning. And the criterion is not exact anymore. So this kind of learning setup is quite different from the one I used initially. But the criterion is still very strict in the sense that for a concept to be pack identifiable, you want it to be identifiable up to an arbitrary bound on the degree of error you're willing to tolerate, regardless of the distribution over the sampling space. So it turns out to be impossible to, well, it seems impossible to prove that the K-reversible languages are pack identifiable because there's no connection at all between the language and the distribution over the sample space. Intuitively, this seems to be the problem. But there are a number of strategies which fix this in ways that you might think are cheating, but they're kind of interesting. So the idea is, in these other paradigms, is to imagine that the sampling distribution isn't arbitrary, but is one that favors certain kinds of evidence. So you might imagine that the distribution of the realistic distribution over human language would be one where the evidence you're likely to get as you draw examples or whatever is most often positive examples, and most often very, very simple positive examples. Things tend to be simple. So imagine you have a probability distribution which favors certain elements in the sampling space. So now this is a risky setup because there's a possibility for collusion between the teacher and the student in the way the distribution is set up. But the idea is, suppose you have a class of languages like this, and you have a distinguishing subset for each language. If you have distributions which guarantee that after a polynomial number of examples, you're very likely to have seen the whole distinguishing subset of the language, then you can get a kind of pack identifiability. That's the idea. And so it looks like we can do this, so I'll get your question in a second. It looks like we can do this for my grammars as well, but it's not done yet. So this is in progress, and if you have ideas here, I'd be interested. But these grammars too, they have distinguishing subsets. Intuitively, in the lexicon, whenever you have a pair of features in the target lexicon which could check each other, so take a set of features which could check each other in the target. If you have a sample which actually connects all of the elements in that set, then that sample will be a distinguishing, if you have samples for every such set, that will be a distinguishing subset for the target language. That subset is finite, and it looks like it's reasonably sized. So this is an open question, but I think we'll get this one. So we still have noise to worry about, but again, if you allow noise to be maximally damaging, then you have trouble, but there are a number of more reasonable models where you have various kinds of white noise where it looks like results will be forthcoming. So I'm optimistic that we'll be able to get more reasonable feasibility results for this kind of learning. And I better stop there. Thanks.
you do about the fact that the zero agreement morpheme is 5 ways ambiguous? Do you not
Right.
analyze it as a morpheme, or so?
Yes.
I walk, you walk.
Right, so the interesting thing about the empty elements in the Chomskyan syntax is they always have a purely structural role. That is, there's never an empty element that means whisper or something like this, you know. So they have a purely structural role, and you can prove that they're grammatical constants in the sense that I alluded to. That is, they're elements that can't be replaced by other things. And so, yeah, I've worked on these at Keenan, and it looks like both syntactically and semantically they're constants. So they play purely structural roles, and if that's true, then we can just treat them in the way we treat these other things. That is, they're introduced in order to put two things together. Intuitively, they're introduced in order to allow things to be assembled for structural reasons. You know, so it reminds, it's like the Lewis Carroll story of the Achilles and the tortoise. Do you know this story? So, yeah, very quickly, the idea is, the tortoise, or Achilles, is trying to convince the tortoise of something and uses an argument of the form if P then Q, and that's one premise, and the second premise is P. And the tortoise says, well, this sounds, you want to draw, you want to do modus ponens there, but yeah, before I'm sure about this argument, I want you to introduce, explicitly the assumption if P implies Q and P, then Q. So the Achilles reluctantly introduces this assumption, but then you have the same problem again, right? So the thing is that there you're introducing assumptions, explicit assumptions, to play a certain structural role. And the roles in this grammar actually are very similar. So if you have two types of things and you want to combine them, and a certain kind of formative will combine them, then you can just infer its existence from the need to make that combination. That's our strategy with those. That's the idea.
I might miss the point, but when you do the unification, would it be possible for it to fail?
It will never fail if the sample is text for a rigid language. That is, if you're looking at the text for a rigid language and you try to unify up to rigidity, it's guaranteed to succeed. But if there's noise in there, or if the target language is not rigid, then you can have unification failures. And this needs to be proven, and we have the proof.
And what do you do in those cases?
So they never happen, right? So
no, if you do have noise.
If you do have noise. So this is where all I say is I'm going to try to follow the example of Anglin and Laird and Kearns, and try to unify only when through the noise it looks like things need to be unified. But I'm just pointing to this. I haven't done it yet. Yeah.
The rigidity condition could have been relaxed, right, without introducing semantics, for example, for verbs that are both transitive and intransitive, allowing like partial rigidity.
Right.
Saying if it has this number of arguments, then it should be consistent, and if it has this number, right?
Yes. A number of these options have been explored in the literature. One idea is you can look at the one learning strategy is unify as far as possible, for example. So this is an idea which has been explored in the literature. So an optimal unifier like this, which just unifies things that will unify, this kind of learning strategy has been explored, and it has some nice properties, but the class of languages that identifies is not so nice. So it's that learning strategy will not, for example, identify all of the two-valued grammars. it will make mistakes and not always be guaranteed to converge on the right grammar. But yeah, these ideas have been explored, and yeah, some people like them. I like to keep things, when I'm doing this kind of work, I like to try to keep things neat as far as, unless I really am pressured by the data to make things messy. So I don't think the data motivate that move. I prefer the move to the semantic enrichment, because I think people really do have this semantic information. Yeah.
This is really cool stuff. I'm thinking though, from one perspective, it might be construed as bad news for the linguist, I'm not sure, which is that it's often seen as a possible constraint on the way human grammars are. Human grammars are the way they are because of learnability requirements. It seems that the kind of grammars that are admitted by this rigidity requirement, as far as I can understand it, are not going to be limited to things which look sensible to a linguist. So that kind of constraint from learnability doesn't seem like it's going to be in these cards. Is that right?
Yes. So many linguists assume that much more is innately given than I'm assuming here. For example, it's commonly assumed that a finite universal set of categories is stipulated, and maybe even certain relations among the categories. So you might be given that tense is a category, and that case is accusative is a category or something. And so we don't need any such thing here. But as far as the question of whether we're likely to get grammars here with this strategy, which would be regarded as crazy by a linguist, I'm not so sure about that, because the grammars we're going to get here, since we're learning from the dependency structures, the grammars are going to be very close to those closely tied to those dependency structures. And so I actually haven't given you the generator for the dependency structures other than the grammars, right? But if we have a learner who can really see the dependencies among lexical items that the linguist thinks are there, then I don't think we'll get crazy results. I think we'll get sensible results. And I'm actually hoping to, I'm interested in the early stages of human language acquisition where inflection is often left out, definiteness is often left out. The neat thing about these grammars is when you leave out tense, it can be added as an extension to the earlier grammar rather than having to modify the earlier assessments of dependency. So tense can be added. We saw it, hanging off as the root in these dependency structures. So I think with reasonable dependency structures, we'll get reasonable grammars. In places where, and this is a very difficult area to study because we don't know what kids notice, really. I mean, cognitively, it's hard to assess what they're noticing.
But I'm not sure that you really need that, because if what you're saying is right, then a theory of what a possible dependency structure would be gives a theory of what possible languages will be.
Yes.
And so, forget about kids, which
Yes.
we always end up doing anyway, why not
Yes.
just now?
Yes.
And come up with alternative,
Yeah,
plausible stories about what kind of dependencies.
Yes, right. Yeah.
And you think that the range of variation. I guess I feel like there are these two ways of instantiating this program. One in which the dependency structures are really limited, in which case I wonder whether you're actually going to be getting too limited a set of syntactic grammars from it to reflect the actual diversity in natural syntax. Or on the other hand, if you're not going to be really highly constraining what the dependency structures are, then you won't have any constraint on what the syntactic grammars are going to be like. So I'm wondering how to...
Yeah, so one thing I didn't acknowledge but should is the way I'm putting a lot of the structured grammar into the dependency structures, this is something lots of linguists wouldn't like doing, you know, so they'd rather say, oh no, it's just stipulated in the innate component, linguistic component that, you know, C is the root and it selects T and T selects Agger. You know, there are people who think that the whole spine of every single clause in every language, this is all just given. And then you just have to figure out where in the given slots things appear. So this strategy, I mean, I could have that effect if I stipulate that in your dependency structures, you'll always find those things given, then I'll find
Well, if you have
grammars.
to add tense in, and then you have
Yeah.
to add an aspect, what order you do it in, and you might end up.
Yeah, and
Stipulate
the
that.
grammars don't block that. You're absolutely right. And so I was able to get dependency structures that get these weird languages with 5 counting dependencies. And so, yeah, you're right. As far as the formalism is concerned, all of these options are open. Yeah. Yeah.
On that, following up on that same exact question, I was wondering if you could speak briefly on the prospect of using negative data, which I know has been controversial in this area, but it seems to me that, say you had super rich negative data, you could define syntactic dependency apart from semantic dependency. And in fact, Chomsky did that in 59 or something, that the definition of a syntactic dependency is a situation where if you change one word, suddenly the sentence is out of the language, then if you fix another word, you can bring it back, you can rescue it and bring it back in. That's a purely syntactic definition. And I'm wondering if you think the ideas about implicit negative data might address this question of what's the right theory of a dependency. In other words, to dodge the two questions that there have been about invoking semantics, could negative data be your ally?
Yeah, probably could be. These are open questions. I'm not sure formal results which answer this, but quite possibly. I should say that in the literature on these K-reversible languages, there are proposals which use implicit negative evidence in a probabilistic sample. That is, roughly the way they work is, since the distinguishing subsets you need are small and highly probable in certain settings, then one thing you can do to, in effect, get evidence that your hypothesis isn't correct is you just draw a large enough sample that your distinguishing subset should be in there. And then if it's not, that's evidence that you've got the wrong grammar of a very powerful kind, and this has been used. And yeah, I'm open to these possibilities. Still, I like the semantic route. I think it's more plausible. And with my robots, so in the thing with the robots, you set things up so it works. You know, so you're not trying to trick the robot. On the contrary, you're trying to help the robot, which is maybe, you know, a bit like the mother-child relation, but I'm not sure. Yeah, there are lots of ways to go here, and many open questions. Yeah.
So you've kind of mentioned robots a bunch of times, and when you were talking about it, I wasn't sure if you meant actually physically instantiated mechanical objects, or whether you're talking about a virtual computational creature in a virtual computational level. And the choice to do one of the other, I mean, they're kind of a big choice in a lot of respects, and it makes assumptions about kind of the nature of understanding. And I was wondering, first, what choice you made and why?
So the main thing, either of those choices would be different from the usual one. That is, usually when people try to study human language, they look at the language in its full complexity. And so either of the choices you described would have the advantages I like, which is I can tailor things to make them, you know, much, much simpler than the usual setting for human learning. But as far as what we're doing, we have, I'm not quite sure how to answer because we have real physical machines, different machines, but they're running programs, they're computing machines, watching network events, and they have a language for describing network events. And so when the teacher sees something happen, well, actually many things happen, but we stipulate a salience order, and the teacher announces what just happened, and as the hearer hears what the teacher said and has been perceiving these same events with the very same salience ranking. And so this is the setup we're working on. They don't have wheels and, or anything. We're not, mechanical engineers, but we are trying to make this really work. And the perceptual, if we're interested in pulling the perceptual environments of these two devices apart a little bit. So the network events of these two devices are not identical, but similar. And so we're interested in this noise question, which was raised because sometimes something will be described which you haven't seen. And we think this is important in the communication setting and something we can get here. In a cooperative situation, which we have, where the robots are trying to communicate, you can get some nice things to happen. So, but yeah, really, this is another talk.
Oh, well, that sounds like a very interesting topic. But, yeah, no, I mean, one of the interesting things about the scenario you just described is that there's some sense of realness of the events that they're observing.
Yes.
And they have like some connection with
yes,
the outside
right. Yeah,
world.
they're real things, and possibly corrupted in various ways. And so we're interested in those things. Yeah.
Actually, thank you.
Yeah.
Any more questions? Well, let's take a speaker. Oh, yeah, there is.
Just a short. So going back to some of the earlier questions, so it doesn't to be anything obvious in your formalism that we force a verb to have only 2 arguments as opposed to, say, 5. Or could you perhaps, do you think that you could perhaps show that if that were the case, learnability would go down the drain, so that learnability provides an answer to that question?
No, it really doesn't. So this goes back to Paul's question. So if you had a dependency structure where 5 things are selected all the time, we'd get that grammar. We'd get a grammar that does that. Yeah. So in a way, it does leave lots of properties to be accounted for, but fewer than usual, right? So usually you stipulate, your verbs have X number of arguments, and you stipulate, the categories are these, and so I'm stipulating a little less than usual, but I still have a bunch that I need to have, and a bunch of them reside in my assumptions about what kinds of destructures that the organism would be able, what kinds of relations among lexical items could be identified by the organism.
It's nice to see these structures coming back.
Yes, it would be it would horrify John.